Hello, everyone. Welcome back for this quick Q&A session. We have today our two lecturers of the day, Javier and Abhinav, and I'm Fabio Scafilimuto. I'm quantum education and developer advocacy EMEA manager, and I have the pleasure to moderating this Q&A session. So as it already happened in the previous sessions, the Q&A sessions, there is a button on your right, so you can post your question, and then, or you can sort of click on other people's question, and this will send them up the list, and I will start from the top to the bottom and read the questions to our two speakers of the day, which we welcome, of course. All right, I guess we can start. See, here sometimes the rate mechanism works a little bit low. So the first question is, it starts with a comment. I actually found this talk very interesting. I have one big internal question. I come from density functional theory, DFT, and first principle approaches. So my question is biased to Gaussian-based sets and completeness of space in quantum devices. So if we figure it out to decode our problem in one Hamiltonian, and we know that the qubit basis set is orthogonal in the Hilbert space, what can you comment about an approximate Hamiltonian whose solution is not known? Would that fall in the type of problems that you handle with overlap? Can you comment on higher dimensional spaces of solutions? The question appears on, yeah.
So maybe I can. Is there any way we can see the full text for the question, or I can start with by addressing the question about the completeness of the basis set. That is a very insightful comment. It is true that in quantum computing we work with discrete basis sets, which are not that are not infinite dimensional, right? So that already poses an approximation. I would say that there is methods to recover so-called dynamical correlation, which is the effects that you didn't take into account because you didn't work with a complete basis set. So I think that there's some techniques, but definitely there's definitely not a one solution fits all for all problems. I think that quantum computers for electronic structure are better suited for a strong correlation, like very strong correlation in discrete basis sets. I hope that answers your question.
Thanks, Javier. I'm not sure if you can see the on the right side the Q&A button. If you want to read the rest of the question, it was a pretty long
okay.
question.
I see it now. Yes.
Yeah,
okay.
You see?
I found that now. Yeah.
Okay, perfect. Then maybe you can also address the second part of the question, since it's the most voted one.
Comment about approximate Hamiltonians whose solution is not known. For the rest of the question, honestly, I'm not entirely sure what you're referring to precisely in terms of the higher dimensional spaces of solutions. If you get a chance to clarify that comment, that would be super insightful.
Yeah. Okay. Then we move on, and then if anybody who wrote the question can just maybe clarify, then we can pick it up later. So the next question is for Abhinav. That's actually specifically written in the under 27 qubit utility experiment. How do you build trust in the results when classical verification is no longer possible? What are the most reliable validation methods at this scale? That's one, and then we have a question for Javier, but I will let first Abhinav reply, and then I will ask the second one.
Hi, am I audible?
Yes.
Great. So the question, if I understand right, is how do you build trust in the results in the 127 qubit experiment when classical verification is no longer possible? Yeah. So this is a great question. And this basically comes down to the. I'm sorry. Is there a lot of disturbance bleeding in for you guys, or is it
Not too much. No,
okay?
not too much.
Not too much. Okay, great. Yeah. So this really comes down to how much trust you can place in your method, right? And this is precisely why it's also important to understand how does one do error mitigation, and what kind of error mitigation methods um, are employed. Can you place rigorous error bounds on the result of the computation that you get from error mitigation? Um, so this is why methods like, for instance, probabilistic error cancellation are very powerful. So you can, even those methods do rely on some assumptions that are made on the noise model, but those are tests that one can perform and build confidence in a lot easier than actually trying to verify the computation directly. So you don't have the ability. So long story short, you don't have the ability to. You might not have the ability to exactly verify the result, but you can place trust in the methods that you used to get the result, and have rigorous error bars on what that result would be. And this is a very, very powerful thing. And yeah, like, and to to offer some comfort, even in classical computing, for decades we've been doing calculations beyond exact verification, but there are a host of things one does to try and build trust in the result. Right? So this is not all that new.
Thank you. I think that's answered the question. We have now a question for Javier. How can sample level processing in SKQD change current workflow in computational chemistry? Could it be easily combined with classical methods like DMET or DMRG?
So that's a very good question. Yeah. So in general, so in sample-based quantum diagonalization or its Krylov variation, or in general with any method in quantum algorithm that targets at finding eigenstates of electronic structure problems, it can indeed be somewhat easily combined with different classes of classical methods. I'm glad that they mentioned the MET, because actually it's in particular as sample-based quantum diagonalization has already been combined with the MET, essentially as a fragment solver. As for DMRG, I would not know how to combine it with DMRG directly, but yeah, it definitely can be combined with other classical methods.
Okay, great. So that's actually a good insight. Thanks for the question. I guess we move on to the next one. For hybrid classical quantum algorithms, so quantum-centric supercomputing, what are the present or future applications in fields other than chemistry or material science? Who wants to take this one?
Maybe I can go first, but I think that in general for scientific discovery, quantum-centric supercomputing is going to be quite powerful. And quantum-centric supercomputing appears in a lot of things that we do. Like, it comes from circuit processing and compilation to different forms of error mitigation. Sample-based quantum diagonalization is one of the examples, but there's a lot of things which would fall inside of the category of hybrid quantum classical algorithms. So I see it as a tool for scientific discovery, and more concretely, one can think of condensed matter problems, high energy physics problems. That's at least my view. I don't know if Abhinav has other.
Yeah. So yeah, as Javier was saying, it's really quite, I'd say, application agnostic. So I'd say that almost for any application that you'd imagine using a quantum computer, you probably can milk a little more by 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 having part of your algorithm perhaps run on on classical HPC. So, for instance, to think of like observable estimation on some quantum circuit, right? And the quantum device is only so much noise that it has noise that enables you to only go up to a certain amount of depth. But then if you try to simulate a part of the circuit on classical HPC, then perhaps you can access a longer circuit depth, right? Now, so everything I've just described right now is quite agnostic to what specific application or field that particular quantum circuit is relevant to. So as Javier said, this I think really extends beyond, and there are a number of examples of error mitigation methods even where one can essentially mitigate on larger circuit volumes by having this classical HPC workflow.
Thank you both. We have a question on the utility scale, a utility paper. So in the experiment this is actually a bit maybe hard to answer without the slides at hand, but we can try. So just slide down. So the question is here. In the experiment presented in the paper Evidence for the Utility of Quantum Computing Before Fault Tolerance, when the magnetization curves are shown, it appears that classical computation becomes increasingly difficult as the angle increases from pi over a to pi over 2. Do the ISO-TNS and MPS methods exhibit slight oscillations or irregularities in the curves? I mean,
Sorry,
if you want to look at the question,
yeah, can I look at the question?
Yeah, it's on the right side. There are 4 little icons. The second from the top is Q&A. You click on that, and that's the question with 4 clicks. Did you find it?
Okay, I find it now. Yeah. It appears that with the ICTS and MPS methods exhibit slight oscillation. Yes. So it indeed. So those particular methods, it so following the paper, that experiment has been benchmarked by a number of other classical simulation groups as well, and there've been a host of other methods. There were verifiable points where we could see that the quantum experiment produced the right result, and these specific methods, the MPS and the ISO-TNS, did not. So we had reason to believe, or we had strong evidence that the quantum experiment was correct at those points. But since the publication of the paper, we've also had many other classical groups also try to simulate the experiment, and they've done a much better job of getting much closer to the experimental data points. So these 2 particular methods do struggle as the circuits, as the entanglement, as the state entanglement grows in the cell.
Perfect, thank you. This got actually 5 votes for this question, so a lot of people notice that in the chart. So we have another question now concerning quantum algorithms for quantum chemistry in general. The common way to do the mapping is to use the Jordan-Wigner transformation, where the fermionic basis is formed by the spin orbitals of the system because it is physically intuitive. In this way, we might end up with quantum algorithms requiring many logical qubits. What is your opinion about using other types of mapping like Bravi, Kitaev, or parity so that we can exploit less qubits? What are the drawbacks of using different mappings?
So this is a very interesting question. I would say that, it is true that when one uses Jordan Wigner, you are kind of ignoring one symmetry of quantum chemistry, which is that you preserve the total number of electrons and the C component of the magnetization, right? So the number of spin up and spin down electrons remains constant. So to describe your problem, you don't need a 2 to the n large Hilbert space. You need a Hilbert space that might be a fraction of it, actually, depending on the number of electrons and so on. Jordan Wigner indeed does not exploit this symmetry, and as you're mentioning, there's Brabby-Kitaev or parity encodings which do so a little bit more efficiently. I would say that the choice of one mapping typically depends on the method that you're using to tackle your problem. Some mappings may require circuits that result in higher entanglement. Some mappings may result in circuits that require more qubits. I think that it is going to be strongly dependent in what algorithm you're planning to run. And the very last thing that I wanted to mention is that I think it's also quite depending on how you want to deal with effects of noise. Jordan Wigner is quite convenient to deal with effects of noise because if your circuits are particle number preserving, like the interacting electron problem is, it is quite easy to identify samples from the quantum device that have definitely been corrupted by noise, because you can very easily just count the number of electrons that come on one of these bit strings. So I would say that also dealing with effects of noise has an impact on the choice of the mapping that you use. But yeah, this is definitely a very interesting and insightful question. Thanks so much.
We have actually another question that just quickly pop up the list, and this about advising the participants. So for those of us without access to large-scale quantum computing, what types of simulations, or more specifically, which physical experiments are worth studying that could be carried out without requiring excessive quantum resources, but where classical computation already begins to struggle? And that's a good question. I just want to, before you guys reply, I just want to remind that, of course, we have an open plan, which somehow makes a certain amount of resources available for everybody to play with and to learn with. But now I leave to the expert replying. Who wants to start?
Yeah. So, am I audible? Again?
Yeah.
Yeah. Okay. So, so it's an interesting question. I'd say that there's of course plenty to contribute even to classical simulation, I'd say, with some knowledge of what quantum hardware can do today with different error suppression, error detection, error mitigation methods. There's certainly a certain budget of 2-qubit gates that are accessible on our topologies, on the order of about 5 to 10,000 gates, I'd say today. Maybe a little more for certain computations. But one can also already begin to ask, what are the kind of circuits that you can execute with this kind of gate count, which are meaningful for certain applications, and yet have state-of-the-art classical simulation struggle? I think this is a very, very important question that, we would love to build this list of circuits of this flavor. So I think there's certainly a lot to contribute in our path from trying to go from utility towards advantage, where one can also contribute meaningfully to the field by understanding and figuring out what kind of applications or circuits can you map in this kind of circuit volume.
Thanks, Javier. Javier, do you want to add anything or?
No, I completely agree with Abhinav. Yeah, it's I think it's also defining where classical computation already begins to struggle is also very tricky to address, right? It depends on the topology of the circuits that you want to run. It depends on the structure of the circuits that you want to run. So, but perhaps a concrete place to start is to study many body dynamics, right? In more than one dimension, that's typically challenging for classical computational methods. But again, I wouldn't want to make too many generalizations because there's a lot of nuances, and in some instances, it might be easy to simulate and so on. But I think that as a starting point, that might be that's what I would suggest.
Thank you. Then we move on to the next question, which is for Abhinav. Do you expect the error mitigation techniques like DNE, direct, and NRE to still be reliable at large scale, since they violate the Rayleigh-Ritz principle?
Yeah. So if I need to understand the question is, in general, even beyond the specific techniques, does one expect error mitigation to be applicable at large qubit counts? So the short answer is in the most general case, eventually one does need error correction. And for tricks like error mitigation, you are going to pay an exponential sampling cost, that goes exponentially with the volume of the circuit. So what that does enable is you can do very meaningful things when the error rates are in the 10 to the minus 4 to the 10 to the minus 3 sort of range, where you can still mitigate fairly non-trivial circuit volumes where you can potentially make classical simulations struggle. But this is going to be in the order of maybe 10,000 to 20,000 2-qubit gates. And so that's probably the range where I would expect one to use vanilla error mitigation. But then I think what one will begin to see are methods that begin to combine error mitigation with error detection and so on, and that is going to be a more continuous path where you will see the use of error mitigation methods even as one tries to build towards fault tolerance.
Thank you. The next question is, even though it's not related to the lecture per se, so it's an advice, I'm reading you work also on NN on quantum states. Can you suggest some references where to start? In which way do you think this field will move? I'm not sure for whom this question is.
I did do some work a few years ago on representing quantum states with neural networks. Maybe it refers to that. But I would say that reference of places to start is the work by the group of Giuseppe Carleo. They do fantastic work on that front, definitely. And I think there's a review paper on I think it's called Machine Learning for Physical Sciences by again Giuseppe Carleo is a co-author. Kyle Kramer is also a co-author. So I would start with the reviews, definitely.
Thank you, Javier. And then maybe if you have it handy, I can post it. And we have a channel Discord which is about resources. So maybe that could be also a good advice that can go there. Right. Thank you for the question. And we have a question about SKQD. Is SKQD also applicable to non-local Hamiltonians with long-range terms?
Yes, it is. It is still applicable to non-local Hamiltonians with long-term range. long range terms. Sorry, there might be some potential pitfalls if one tries to do that. Again, the assumptions for SKQD to converge with a polynomial amount of quantum and classical resources is a sparsity of the ground state and a non-exponentially vanishing gap. So as long as those are guaranteed, even if your Hamiltonian has non-local terms, I think that's okay. One difficulty might be with implementing the time evolution on a given device topology, right? Which may result in having to use relatively long CNOT ladders to implement these longer range terms via trotterization. But I would say that is very problem dependent, and I would say, yeah, it's probably, I don't see any issues with applying it.
Okay, thank you, Javier. I know you have an hard stop, so I guess we can just thank you now, and then Abhinav, if you can stay a few minutes longer with maybe we take another couple of questions. Perfect, thank you.
Yeah, thanks so much.
Thank you,
Bye
Javier. Bye. So we continue with another couple of questions. So thank you for the detailed presentation. With respect to quantum-centric supercomputing, what classical distributed computing, any known platform, is used to process big classical data? And what is the scale of this classical data?
This probably would have been a better question for Javier to answer. But maybe I can say a few things. So it might be useful to just look back at some of the SQD and the SKQD papers. But you're still looking at diagonalizing matrices, of dimension 10 to the 8, 10 to the 9, and so on. There are a lot of bit strings that you're getting from the quantum device there, and you're trying to use a subset of those to try and diagonalize and access your ground state. So that can be very large, and I think Javier might have touched upon this in his lecture. But yeah, there are aspects of trying to do a back and forth between quantum and classical, where you feed back the energy from the diagonalization to determine a new quantum circuit to run on the quantum hardware, and then you have that back and forth loop, like in a variational quantum eigensolver. Yeah.
Thank you, Abhinav. We have another person who looks for advice. In this case, the question is where can I find use cases or problems of quantum computing for research projects? That's a very very big question. If you have some ideas or some input. Otherwise, I think we can also advise people, of course, to look into our learning page. That's maybe not a new project, but can be used as an inspiration for other projects. We have courses, tutorials that look into different applications of quantum computing. Some of which have been already have been covered by lectures. For example, we have a tutorial about FQD. So I think this could be also used for inspiration for research projects. But Abhinav, if you have any other recommendation.
Yeah, absolutely. I mean, certainly, I think there's a huge community of colleagues at the summer school. Certainly, ask them as well. That's one. I think Javier kind of alluded to this one. I think for the immediate near term, certainly something in the realm of many body quantum dynamics is very attractive in terms of potential use case where one can actually learn something about new physics that may have been inaccessible to with just classical simulation alone. But no, this is there are plenty of domain experts trying to figure out those specific use cases. This is a tremendous research area. Areas going from quantum simulation with quantum chemistry, material science, high energy physics, condensed matter, and then even to areas like optimization and finance um, um, and yeah, machine learning even that a lot of people are exploring. Almost uh, maybe just typing these keywords with quantum in your favorite search engine might already just pop up some reviews of what people are doing in all of these different areas. Within the whole within the way we organize also a lot of this work at IBM, there are examples of working groups for specific domain areas, and there've been examples of white papers or review documents that have been put out for where people expect to have uh, you know examples of advantage in certain areas and things like that. So or at least examples where there's the hope that this might be accessible for the near term, uh, but they they know that traditional classical methods struggle there. So those are also another that's also another good place to look. These white papers certainly exist for high energy physics, for material science even, and for optimization. I think you should be able to find it on the archive, or you guys can share it in the resources.
Yeah, that's a very good point. We have now a question again in the paper evidence for utility for the utility of quantum computing before fault tolerance. Magnetization was studied for different angles in a 2D spin lattice system. Would it something dropped here? Would it be worthwhile to study magnetization in a 3D system, for example, spin arranged in a cube or something similar?
Yeah, so in that particular experiment, we were essentially studying the dynamics of a spin lattice, a 2D spin lattice that shared the topology of the hardware, right? So now trying to map this for a 3D system on a planar superconducting device, that mapping, is obviously a much harder thing to do. One could imagine. I mean, certainly, like, is it worthwhile? Absolutely. I mean, I think for sure people are interested in this. Particularly as you want to simulate actual materials, uh, uh, which are often 3D or modeled as 3D systems. Uh, so there are other platforms, quantum simulators, which let you more natively perform quantum simulation of 3D systems. Um, uh, on the superconducting platform, it's a little non-trivial, I'd say, but certainly it also is meaningful because as you increase the dimensionality, you also tend to make classical simulation a lot harder. So it's typically the kind of thing that one does to try and uh, search for quantum advantage.
Thanks. I think we take maybe one or two more and then we close the session. We have a question about SQD, so would have been more for Javier, but perhaps we can answer it as well. Is the sample-based quantum diagonalization methods essentially perturbation theory?
I don't interpret it that way. I look at this more analogous to what are uh, referred to as like SCI, or selected configuration interaction methods. So essentially, the high level idea, the way I like to understand it is if you have an n qubit system and you have 2 to the n different possible configurations, right? And trying to diagonalize a matrix that's 2 to the n by 2 to the n is extremely hard. But even classically, what people try and do is say, actually, the ground state probably isn't something that covers all of these different configurations. It's a much smaller subset. And if you had access to that subset, then you have a much smaller Hamiltonian to diagonalize over, right? And now, how do you get access to that small subset? In the context of SQD, you're running a quantum circuit to get those samples that point you to that smaller subset. So that's how I view SQD. So this isn't really perturbation theory.
Yeah, I also am not an expert, but I fully agree with your interpretation. I don't think that's perturbation theory. I think we take the last one, which is about more condensed matter physics. Due to strong correlation, metals are difficult to study using traditional computational chemistry. Have you performed calculations on metals? How do periodic boundary conditions come into play in quantum computers? Are you aware of any study on metals, and if you know if boundary conditions how come into play when we perform simulation?
This is really a question, I think, for Javier. I'd probably encourage you to send him an email if you're interested in this.
We have also a Discord server with many channels, and I think people can also ask questions. And I think that's a very interesting question. I'm also not sure if there is any calculation on simulations on metals, so there could be something interesting to ask there. And then maybe take the last one. Checking this is a question for Javier. Solutions. Maybe this one is. Why are hybrid solutions mostly more efficient than quantum-only solutions? So why quantum plus classical rather than only quantum?
So it's okay. Once I don't necessarily want to generalize, but I think maybe the person asking the question is referring to specific examples that they've seen. Certainly in the context of the quantum chemistry simulations, right? Probably the best bet for those kinds of problems prior to SQD was the variational quantum eigensolver, and those methods have a big challenge from the number of terms that one has to sample. That typically goes as m to the 3 or m to the 4. So this requires you to sample over many different basis transformations at the end, or it requires you to sample many poly strings. Said a little simpler, and that just becomes very hard to do. In addition to that, then you are also sensitive to noise.
I think we lost Abhinav. Hopefully
can you hear me? Can you hear me?
Great. I believe Fabio has dropped. Is there anything else that you would like to close on before we end?
Can you hear me?
Yes.
Okay. I think Fabio dropped for me. Okay. So I think folks. Okay. people. So I'll just finish my response. So the alternative was something like the variational quantum eigensolver. So one, you have the number of poly strings that you have to measure. That really grows up. It grows. It doesn't grow exponentially. It actually grows polynomially, but it still is a very large number for the kind of scales you're interested in. And in addition to that, you then have noise that you have to deal with also biases, the values of those expectation values of those poly strings that you want to measure. So this really set the largest scales of VQ, the largest VQE experiments for chemistry to be much smaller than 20 qubits or something. Why have methods like SQD been so successful? Because one, a large part of a fairly non-significant part of the computation you're able to push off to do classical. There is a certain amount of error resilience almost to the algorithm, because you can use configuration recovery and methods like that to correct for even noisy or incorrect bit strings. If you had useless bit strings, almost they don't have an impact on the quality of your energy, but you're just paying more classical cost. So in that context, one, it solves the measurement problem of VQE, and two, it has this inbuilt noise resilience. So both of these made it very attractive to have that kind of jump where one could go from quantum chemistry on near-term devices, being stuck at the under 20 qubit level, now to almost 80 qubits. So that's been one of the reasons for the big success of these more hybrid methods.
Great. Fabio, welcome back. I think or not welcome back. I think that is a great way to close today. Thank you so much for joining for the Q&A, everyone. Really appreciate it. Any questions that may still be pending, feel free to go ahead and ask them in the Discord, and we will be active in there. Beyond that, thank you so much for joining us today at the Q&A, and we will talk to you all soon.